Okay, now we are off to Chapter 10, the DC circuit analysis and Kirchhoff's laws. So now we're going to be looking at the applications of the laws and using the math that we're learning to apply them. So in this section, we're going to concentrate mostly on Kirchhoff's laws, Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL. And then we're going to wrap up with the polarity and using that to help us solve circuits. So we're going to use each of these laws to do the math that we've learned and the applications. Kirchhoff's current law, or KCL, describes the behavior of electrical charges in a circuit. So when we talk about current flow, we're actually talking about the potential or the value of the charges as they move through a circuit. Typically in electronics, using pipes and water flow is a good analogy to understanding this. So charges moving in a given direction in an electrical conductor are analogous to water flowing through a pipe. And typically we look at the water as it's flowing past a particular point. So in this case, open pipe, no restrictions, no resistance. We have 10 gallons per minute flowing past a point where we have 10 gallons per minute as we move past that point. So in this case, the flow of charges in an electrical circuit, we use an electronic term of current. So that's the movement of the charges. The potential on the charges is the voltage. The number of charges per second, or current, flowing in a conductor then must equal the number of charges flowing from that point. So we have a number of charges flowing, and that number of charges equates to 3 amps. It's not the 3 amps is not the value of the charge, but it equates to 3 amps of current. Current is kind of like the pressure of the current flow of those charges moving through the pipe. The algebraic sum then of the currents into and out of a point then must equal 0 if the currents toward that point are given an arbitrary positive or negative value. So in this representation we can see we've identified the current flowing into the point, which happens to be this demarcation, this dotted line, flowing into that point, that would be positive. The value flowing out of it would be negative, and those two values have to match. So I1 equals I2, or the sum of the two equal 0. According to Kirchhoff's current law, then, the magnitude of the current must be the same at any point in a closed loop. Okay, so in looking at this simple circuit here where we have a couple of lamps in the circuit, we've got a source which would be identified by the amount of voltage, and we have the amount of current that that voltage produces flowing through the lamps and back into the source. So for a series circuit, we have a circuit that there is only one path for current. We will later see that the current can be divided up and create values that are less than the total amount that we started with. The sum of currents then toward a junction must equal the sum of the currents leaving that junction. So if we look at this point here as the junction, we end up with 3 currents. The current number 1 flowing to that point, current number 2 flowing beyond that point, and current number 3 flowing beyond that point. At this point, we can see that what we have is the current splitting or dividing up along the 2 paths at that point. So I1 could be considered a total current, and then I2 and I3 would be the sum of those 2 currents as they leave that point. The sum of the currents toward the junction must equal then. Now we can see if we change the representation around a little bit, we have 2 parallel paths where we have 2 amps and 3 amps flowing on each of the paths for this network. They sum at this point to give us a total of 5 amps. So all the currents flowing into the point must sum to some total current. An electrical circuit that has both series and parallel circuit characteristics then are called series parallel circuits. So as we go through doing different types of characteristics and analysis, we will typically start with series, we will move to parallel, and then we combine the two into a series parallel. So this is really a series parallel. What makes it that? Well, we have lamp number 1 coming out in series. We have lamp number 2 and lamp number 3 dividing the current up into a parallel branches or network. The current then recombines at point C, because we can see the current is moving along the bottom of the screen. It splits at point B. Part of it goes to lamp 2. Part of it goes to lamp 3. It recombines at point C, and we have the total current through lamp 1. If a charge travels around a closed path in an electrical network and returns to its starting point, its net potential then, or change of energy, must be 0. So everything we looked at to this point was Kirchhoff's current law. Now we're going to look at Kirchhoff's voltage law. KVL expresses the law of conservation of energy and can be stated as, around any closed path, the sum of potential rises must equal the sum of potential drops. So if we put this into symbology, the summation sign E, the potential, has to equal the summation sign V, the potential drops. Potential rises then in an electrical circuit energy sources could be, in this case, 110 volts supplied to by the local electric company, a battery, or some other source. It doesn't matter where this source comes from. We're going to say that it has some value in voltage, and the current then, in this case, will go in two different directions. But you will notice here, from point A to the reference point, in this case, it's telling us we have a 10 volt potential from that source. You need to get used to understanding in a circuit like this, and this is a very simple circuit that has two branches in parallel, the voltage across lamp 1, V2, is the same as the source. The voltage across V1, 10 volts, is the same as the source. So in this configuration, in looking at this, you can quickly ascertain that from A to ground, or the reference point, I have all of the source energy, 10 volts, being applied. If I put a meter at point A and a meter at point reference point down here, I would measure 10 points. I could move that anywhere along the top line of the schematic or anywhere along the bottom line of the schematic, and I would get 10 volts. It would not change. So the algebraic sum of electromotive force, EMF, and the voltage drops, V, around a closed path equal 0. Okay, so this is just telling us that all those voltages measured have to equal 0. Both lamps L1 and L2 are connected across the electrical energy source. So you got to get used to that term. The voltage isn't flowing through this circuit. The voltage is across the two reference points in this circuit, point A and ground. Kirchhoff's voltage law tells us that any closed path, the EMFs and the voltage drops must equal 0. So if we look at loop 1 on the left side, we have the source equal to the drop, V1. If we look at loop 2, we have the source equal to V2, the voltage drop across L2. So, applying Kirchhoff's voltage law then, the source voltage, E, has, in this case, equals the drop, V1, and equals the drop, V2. Therefore, V1 and V2 are the same value. In this case, it is, in fact, the applied voltage of 10 volts. In a parallel circuit, then, the voltage drop is the same across each branch. So in this case, V1 and V2 are the same, and we can say then that the voltage in the network is in fact 10 volts. the total current into and out of the branches equals the sum of the individual branch currents. So in this case, the total current, that value applied to the source, I total, would equal the current in loop 1 added to the current in loop 2 and any other loops that we would have in this circuit, because we could add another one here, and that would be loop 3, and then add that to the total would equal to the value associated with the total of current. So any other current in the network. And that's what that N stands for, the additional current in the network. We have an electrical energy source connected in series now with 2 lamps. So we've only got one pathway for the current to flow across L2 and L1. The electrical energy raises the potential energy of the charge to 10 volts at point A. There is only, though, one path for the charge to take when the current starts flowing. So the lamps L1 and L2 become a drop. They are essentially a resistance in this circuit. Each one will drop an amount. Well, if I have 10 volts total, and we say that lamp number 1 drops 4 volts or 6 volts, then by default, lamp number 2 has to drop the other 4 volts. In a series circuit, then, the current is the same throughout the circuit. So there's only one path that can flow from the source to point A, across the top into L2, L1, and then back to the source or the common. The sum of the voltage then must equal the electromotive force EMF. So all of the drops have to sum to the original voltage applied. So if we take an example here, find the magnitude of the voltage across lamp number 2, where the applied voltage is 30 volts and the drop across lamp number 1 is 10 volts. We can, using the Kirchhoff's voltage laws, determine the value of the unknown on V2. So in this case, since we know that the EMF has to equal the sum of the drops, rewriting the expression as V2 is equal to voltage 1 minus the 30 volts or EMF, we end up with 20 volts for our unknown value. In this case, we added another resistor, R1, R2, and R3. We want to find the voltage drop across R2, given that R1 is dropping 5 volts, R3 is dropping 7 volts. Again, we use Kirchhoff's voltage law. We plug it into the relationship, solve for V2, and we end up with a value of 8 volts dropped across R2. Kirchhoff's voltage law then is satisfied because part of the source voltage is dropped across the circuit between points, in this case A and B, which is the same as resistor R1 and R2. You'll notice R1 or R2 and R3. R1 is not part of the parallel branch. R1 at this point is acting like a series pathway, and it would be passing all of the current. But at point A, the current splits depending on the value of the resistance R2 and R3, and would give us back the amount of drop that would occur at each of those points. The current recombines at point B, and it returns to the source. Polarity then has to be observed when we solve these types of problems. And polarity is based upon 2 conventions of current flow, electron flow and conventional flow. And you'll notice that the flow here is, one says that I have current flowing in this direction from the battery into the resistor R1, R2, and R3. In this case, the current is flowing from negative to positive. In conventional flow, it is from positive to negative. It's just a matter of picking a convention and sticking with it. Suppose we were interested in the potential at one point in a circuit with reference to another point. Well, what does that mean? What is the potential at point A with respect to the common? Well, with respect to means nothing more than reference to. In this case, since we are looking at the voltage across the battery, the source, 30 volts, the resistor down here where we have a voltage drop of V4 is going to determine that we only have 10 volts across A and the reference point. The voltage drop across V4 by inspection then becomes 20 volts if we know that we only have 10 volts here. So we get used to looking at these type of simple circuits, and it helps us when we start adding more series and parallel branches into a circuit. And sometimes the geometry can look daunting, but it actually, once you get used to doing this, becomes very, very simple. Time consuming, but step by step becomes very simple.